everyone, today we are going to learn more about normal distributions by taking it to a whole new level called a standard normal distribution. Before we get started, I would like you to please go ahead and complete this quick warm-up. I would like you to please factor x squared plus 7x plus 10. Then we have x to the fourth power minus 625. Then we have 27x cubed plus 1. And then 2x squared minus 10x. Please pause the video and factor each one of these on your own. And when you have an answer, please restart the video and we'll see how well you did. All right, so for the first one, we split it apart into two parentheses. And I'm going to split apart the x squared into an x and an x and ask myself what two numbers multiply to equal 10 but together add to equal 7? And that is a 5 and a 2. So we have x plus 5 times an x plus 2. Next, whenever you have an even exponent and it's being subtracted by a perfect square, that's called a difference of two squares. Or in other words, a dot. So I'm going to split apart the x to the fourth into an x squared and an x squared. And then I'm going to take the square root of 625, and that's going to be a positive 25 and a negative 25. X squared minus 25 is also a dot. So we have double dots in this case. So I'm still going to have x squared plus 25. This is not a difference of two squares since they are being added together. But I'm going to split apart the x squared minus 25 into an x plus 5 and an x minus 5. And that is your full factorization. Number 3, we have 27x cubed plus 1. This is what we call a sum of cubes. And that's because the first term is a perfect cube, and the second term is also a perfect cube, and they're being added together. So our strategy is to break this apart into a binomial times a trinomial. The cube root of 27 will go into the first position, and that's a 3, and the cube root of x cubed is x. The sign in the middle is a plus, and the cube root of 1 is 1. We're now going to use that binomial and that little phrase called SOPs to come up with our trinomial. So we're going to take our first term and square it. 3x times 3x is 9x squared. Opposite of a plus is a minus. Product, 3x times 1 is 3x, and then square. 1 squared is positive 1, and that last term is always going to be positive. Square, opposite, product, square. And finally for number 4, 2x squared and 10x. Although this is a difference, this is not a difference of two perfect squares, so instead we're going to use GCF. So I'm going to factor out a greatest common factor, and 2 and 10 both have in common a 2, and x squared and x both have in common an x. So my leftovers is going to be an x minus 5. And that is my answer. There is nothing further for me to do. So hopefully you did well in the warm-up. And if you are still struggling with factoring, please make sure that you have a conversation with me as soon as possible so that we can go over factoring and I can make sure that you do well on the remaining tests, because factoring is not going away. So our learning targets for today is for you to be able to say, I can calculate the z-score for any given data point, whatever that data value is, and I can use z-scores and a z-table to find the probability that a randomly selected value lies within certain standard deviation boundaries. So we are going to be learning about this standard normal distribution, but before I start talking about what all of these values mean, I'm going to skip down to example number 4, and we're going to analyze example number 4 using the same strategies as we did in the last video. So in our last video, we learned that if we identify our mean and if we identify our standard deviation, we'll be able to identify any sort of value. We can change any value to a standard deviation. How many standard deviations above or below the mean is that data value? So in example number 4, it says a survey of a group of women found that the height of the women is normally distributed with a mean height of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a woman is at most 58 inches tall. Now that language of at most means that they are 58 inches or shorter. At most means that the most that they are 58 inches. So the symbol that we use for at most is less than or equal to, because you can't be any more than 58 inches. So we want to figure out what is the probability that a randomly selected woman, her height is less than or equal to 58 inches, which is pretty short. That is so short, it's shorter than me. So let's go ahead and look at the information they gave us. They told us that the mean is 64.5 inches. So that's our x-bar of 64.5 inches. And our standard deviation is 2.5 inches. So let's go ahead and figure out where 58 is with respect to 64.5. So I'm going to take 64.5 and I'm going to subtract one standard deviation, which is 2.5. And 64.5 minus 2.5, that is equal to 62. Okay, so we haven't quite made it there yet to 58. So now I'm going to take my mean and I'm going to go 64.5 minus another 2.5. So that's 2 times 2.5. So that's 2 standard deviations below the mean. So 64.5 minus 2 times 2.5, that is 59.5. So we haven't quite made it to 58 yet. So let's go ahead and do another standard deviation. So I'm going to write 64.5 minus 3 times 2.5. And if you were to put that into your calculator, you would end up with 57, which we want 58. So how on earth do you figure out what this probability is? Well, that's where z-scores come in, and that's where the standard normal distribution curve comes in. Because not all data values are going to be exactly on the 1, 2, 3 mark of standard deviations above or below the mean. A lot of times, and most of the time, you're going to be somewhere in between. So let's go ahead and analyze this standard normal distribution. So in order to combat this issue, mathematicians came up with the standard normal distribution, and what they did is they adjusted the mean to be the number 0. So instead of your mean actually being the number 0, they changed it to what we call a z-score, and they said, let's call the mean 0. This is where we want to start. And any number, the number 1, 2, and 3, -1, -2, -3, represent standard deviations, exact standard deviations above and below the mean. So 1 represents 1 standard deviation above the mean, 2 represents 2 standard deviations above the mean, and so on. Below, negative. -1 means 1 standard deviation below the mean. 2 standard deviations below the mean is -2, etc. So a standard deviation is considered the number 1. So we have a mean of 0 and a standard deviation of 1. And notice that all of these are equal to the letter z. The letter z represents our score, the number of standard deviations that a value is above or below the mean. And it has a formula, x minus x bar divided by standard deviation. This is a formula that I need you guys to please make sure that you know and study, because this formula will tell you how to convert any data value, which that's what x is, to a z-score so that we can find it on our curve. Where is it located? So we're going to use this formula to transform x values with a mean of x bar and a standard deviation of lowercase sigma. So we're going to actually use those values that come from our example, whatever our story problem is, and we're going to convert it into z values where our mean will now become 0 and our standard deviation will now become 1. So the z value for a particular x value is called a z-score, and it represents, like I said, the number of standard deviations that an x value lies above or below the mean, which we call x bar. Now z-scores have to be rounded to the nearest hundredth. Otherwise, you won't be able to use this table that you guys picked up in class. So we're going to identify how to interpret or how to find your z-score, but it has to be to the hundredths. Why? Because this table requires you to have your z-scores in the hundredths place. Now, if z is a randomly selected value from a standard normal distribution, then you can use the table. It's not below. It's the table that is pink. So I'll call it the pink table that we picked up in class. You can use the pink table to find the probability that z is less than or equal to some given x value. So z has to be less than or equal to. It can be less than, it can be less than or equal to. So I'm going to say right here that if you see the symbol less than, that also works. So it also works with less than. So if you have a less than situation, that's fine. Because the space of the equal to, that's indicating like the space of a line right there, the area of a line is 0, so it's not going to add or subtract anything. So I'm just putting that out there. So let's go ahead and pretend that I want you guys to identify the probability that z is less than or equal to, let's go with 2.45. All right, so on your z table, there are two sides. There is the side that has a lot of shading, and then there's the other side that has a little bit of shading. On the side that has a lot of shading, notice that your z-score is well past your mean. So this is where your mean would be located. We'll call it 0 because that's where mean is. And notice that it's above it. So that indicates that we're talking about positive z-scores. So these are positive z-scores. And how you read this table is you have columns and you have rows. Notice that your column is all written into the tenths place, 2.1, 2.2, etc. And notice that your horizontal table is written into the hundredths place. So if I wanted to find the probability that z is less than or equal to 2.45, that means 2.45 standard deviations above the mean, then I'm going to go and identify where 2.4 is first. So this is my tenths place, and this is my hundredths place. So this is the tenths place and the hundredths place. I'm going to go to where 2.4 is first. So 2.4 is right here. And then I'm going to count over. This is 2.40, 2.41, 2.42, 2.43, 2.44, 2.45. So my probability that z is less than or equal to, if you were to draw a picture of that, what does that look like? We would have a mean of 0 and a standard deviation of 2.45. So here's 1, here's 2, here's 3. 2.45 is going to be right here. So this is 2.45. And we want the values of z to be less than or equal to that. So I'm talking about shading all of this. Notice that that's a lot that is being shaded. And according to my z table, the probability that a value is less than or equal to 2.45 is 0.9929. And that is it. You're done. There's no work for you to show. There's nothing to add. There's nothing to subtract. There's nothing that you need to do. So that is the probability that z is less than or equal to 2.45. We could also go the other way and go the probability that z is less than or equal to negative 2.45, in which we would do the same exact thing, only our picture is going to be a little bit different. So here's where our mean is. And then negative 2.45, here's 1, 2, 3. 2.45 is about right here, so negative 2.45. And we want it to be less than negative 2.45. So that's a really, really small area. And since our z-score is negative, I'm going to go to where the negative side is. And notice that right here is about where the your mean is. And your z value is on the other side. It's a smaller portion of it. So these are your negative z values. Negative z-scores. So I'm going to go down here to where negative 2.4 is. So these are your tenths place once again. And up here are your hundredths. And I'm going to go to where negative 2.4 is, and then I'm going to count over to where 0.5 is. So that's negative 2.40, 1, 2, 3, 4, 5. And that value is 0.0071. And that is the probability that you have a z-score less than or equal to negative 2.45. If we were to look at this example right here where it says the table shows that the probability that z is less than -0.4, notice that it's not written in the hundredths place. So it might be in your best interest to rewrite that as z is less than or equal to -0.40. So we would go to where -0.40 is. We go down to where -0.4, and then over the first one is 0. Notice up here we see the 0, 0. And we end up with 0.3446. And if you were to draw a picture of what that would look like, we would recognize that our mean would be at 0, and -0.4, well, we call this one standard deviation. We would call this -0.4. And we want to shade everything below it. So that clearly that is less than 50%. So it says you can also use the standard normal table to find the probabilities, which is exactly what we're talking about here. Whenever you see that P in front, that's probabilities. To find the probabilities for any normal distribution by first converting the values from the distribution to z-scores. So that is always going to be your first step, and the way to convert it to z-scores, once again, is for you to use this formula, x minus x bar divided by standard deviation. So let's go back to example number 4. Clearly we know that 58 is not, it's going to be somewhere in between 2 and 3 standard deviations below the mean, but we need to figure out exactly where it's at. So we're going to find the z-score corresponding to the x value of 58. So I'm going to write z is equal to 58 because that's my value, and I'm using the formula z is equal to x minus x bar divided by standard deviation. I'm going to take x, which is 58, minus x bar, and my x bar is 64.5, and I'm going to divide it by my standard deviation, which is 2.5. So when you do that, 58 minus 64.5 divided by 2.5, we would simply put that into our calculator and always round to the nearest hundredth. And when you put that into your calculator, you're going to end up with -2.60. So what does -2.60 represent? Well, it means that 58 inches is 2.60 standard deviations below the mean. So now we're going to use the standard normal table to estimate the probability. Now, notice that originally I had the probability that x is less than or equal to 58. Now that we had to change it to a z-score, we're going to rewrite this language as the probability that z is less than or equal to our z-score, which is -2.60. I'm going to be looking for you to translate or transition your probability statement to z-score, to working with a z-score statement. So I'm going to put, or go to my table and look for -2.60. So I'm going to go to the negative side. I'm going to look for where -2.60 is located. So here is -2.6, and -2.60 is 0.0047. And that is it. That is your answer. There's nothing further for you to do or for you to show other than a little picture. So I need to draw my little picture. That's important that we always draw our pictures. So my mean is 0, and I'm looking at 2 standard deviations below the mean. So here's 1, here's 2, here's 3. 2.6 is closer. So I just am going to write down -2.67, and we want, I'm sorry, 60, excuse me. And we want the values less than or equal to -2.60, and so that's where I'm going to shade. You do not need to label any of these. You just need to always show your mean and then always show your focus. What is the value that you're focusing on? Let's go ahead and flip the page. For our next problem, we have a normal distribution has a mean of 65 and a standard deviation of 6. Find each probability. So for these problems, we know that our x bar is equal to 65 because they told us that that's our mean. And we're told that our standard deviation is equal to 6. And our first thing that we need to do for each one of these is we need to convert each number to a z-score. That is always your first step. You need to convert them to z-scores because we are assuming that they are not exactly 1, 2, 3 standard deviations above or below the mean. The next thing you need to do is you need to make sure that you have a statement written with a less than or equal to symbol. So make sure that you have a less than or equal to symbol so that you can actually use your table. If you have a greater than or equal to symbol, then we're going to work with complements, that information where we work backwards, that 1 minus, just like we did in the last lesson. And then step 3 is we're going to use the table. Use the table to find your probability. And then, of course, make sure that you draw a picture to represent your information. So I'm going to be looking for a lot of different pictures. Okay, let's go ahead and look at letter A, and I'm going to draw a line for space purposes to separate my information. So let's go ahead and look at letter A. For letter A, the first thing I need to do is I need to change 61 to a z-score. So that is step number 1. So I'm going to change it to a z-score. So I'm going to write z is equal to my value, which is 61, minus my mean, which is 65, divided by my standard deviation, which is 6. 61 minus 65, that is -4, and -4 over 6 is -2/3. But I want that to be written as a decimal rounded to the nearest hundredth. So that's going to be -0.67. So the next thing I'm going to do is I'm going to rewrite my probability statement using a less than symbol and the z-score, using an actual z. So I'm going to write this as the probability that z is less than or equal to -0.67. If I were to draw a picture of what this should look like, drawing a quick sketch. My mean is located at 0, and -0.67, if I were to say that this is 1 standard deviation below the mean, -0.67 is about right here. I'll write that as -0.67. And we want the values less than or equal to that, so I'm going to shade everything below. Okay, so now let's go ahead and take out our table. I'm going to go to where -0.67 is located. So here is -0.06, or 0.6, and I'm going to go over to where 7 is located. So it looks like that's the third from the last column. If I were to come up here to where my columns are, it looks like it's in the third to last column. And if I were to go on over, I believe that that's going to be located at 0.2514. So 2514. And that's my answer, 2514. And that is it. There's nothing further for you to do. Let's go ahead and look at letter B. For letter B, this is a little bit different. Notice that we have a greater than symbol. So remember that we want them to be written as a less than symbol, or a less than or equal to. So that means that we're going to be working with complements. So the first thing that we still do is always convert each to z-scores. So I'm going to write z is equal to 58 minus 65 divided by 6. So 58 minus 65, that is -7 divided by 6. And if you were to put -7 divided by 6 into your calculator and round to the nearest hundredth, that is -1.17. So we want to figure out the probability that z is greater than or equal to -1.17. But it needs to be less than or equal to. So we're going to be working with complements. So that's going to be 1 minus the probability that z is less than or equal to negative 1.17. That's what our complement is. 1 minus, and then the opposite symbol for, or the opposite inequality symbol. So what does this look like? Well, this would look like a lovely little standard normal curve. Here's my 0 and negative 1.17. Well, here, let's say that this is 1, negative 1.17. We'll say it's right here. And we want to shade everything that is greater than or equal to that. So I'm going to shade everything above negative 1.17. So now I'm going to go 1 minus. This equals 1 minus. And I'm going to identify what the probability of negative 1.17 is, what that value is. So I'm going to go to where negative 1.1 is. So here it is. And then I want negative 1.17. So it's 0, 1, 2, 3, 4, 5, 6, 7. And that is located at 0.1210. So it's going to be 1 minus 0.1210. And when you put that into your calculator, you're going to end up with 0.8790. And that's your answer. There is nothing further for you to do. So once again, if you have a greater than or equal to symbol, you have to do the 1 minus in order for you to come up with the probability that you are actually intending to look for. And like I said before, you need to make sure that you draw a picture, draw a sketch of what the relationship is taking place, or what relationship is taking place. Let's go ahead and look at letter C. This is one that I'm going to star. I want you to please make sure you pay attention to what I say, especially for example numbers or letter C, because this one will definitely be on your test, and it can get kind of tricky, so just pay attention. We're going to do the exact same steps as before. I'm going to convert 75 and 81 to z-scores. So that is step number 1. I'm going to write z is equal to 75 minus 65 divided by 6, which is 10 over 6, which is 1.67. And I'm going to convert 81 to a z-score, so that z is equal to 81 minus 65 divided by 6. 81 minus 65 is 16, and 16 divided by 6, that is 2.67. So now rewriting this in terms of z's, I want to find the probability that my z-score is in between 1.67 and 2.67. So what does that look like on a table or on a graph? Well, on a graph, here's where 0 is located, here's where about 1 is, here's where about 2 is, and here's where about 3 is. 1.67 is going to be located right about here, so we'll call that 1.67, and 2.67 is located right about here. We'll call that 2.67. So I am interested in just this little space right there. So how do we figure that out? Well, what I can do is I can find the probability that z is less than or equal to 2.67. So what that's going to do is it's going to find the entire area of everything from 2.67 and beyond. So that's what I'm going to start off with. You always start with your larger z-score, and then you're going to subtract away your smaller z-score. So I'm going to rewrite this as the probability of z being less than or equal to 2.67. So if we're talking about the probability of z being less than 2.67, I'm shading everything below. But I don't want everything below, because I don't want anything that's less than 1.67, because that part's not shaded. So I'm going to take away the probability that z is less than or equal to 1.67. So I'm going to explain that again. What I did is I took my larger z-score, which is 2.67, and I can use my z-table because it represents everything that's shaded below, and I can find out the probability that z is less than or equal to 2.67, and that represents this entire space. But I don't want the entire space. I just want everything until 1.67. So anything, any value, any shading that would be less than 1.67, I want it to be taken away. So that's the reason why I'm going to write minus. It's always your larger z-score minus your smaller z-score. So that's why it's very important that you use less than symbols, and very important that you always write it in numerical order. So let's find the probability that z is less than or equal to 2.67. So I'm going to go to my positive side, and I'm going to go to where 2.67 is, and 2.6 is right here, and 2.67, I'm going to count. This is 0, 1, 2, 3, 4, 5, 6, 7. So that's 0.9962. So this equals 0.9962 minus, I want the probability that z is less than or equal to 1.67. So I'm going to go to where 1.67 is located. So here's 1.6, and I'm going to go over to 1.67. So that's going to be 0, 1, 2, 3, 4, 5, 6, 7. And that is 0.9525. So that's what I'm going to subtract. 0.9525. And when I subtract these two numbers and I put it into my calculator, I'm going to end up with the answer of 0.0437. And that is the probability that a randomly selected value is in between 75 and 81, or in between 1.67 standard deviations above the mean and 2.67 standard deviations above the mean. Let's go ahead and look at example number 6, and it's going to use the same skill that we just did in letter C in order to do example number 6. So it says a normal distribution has a mean of 20 and a standard deviation of 0.25. We want to use the standard normal table to find the probability that a randomly selected value is in between 19.4 and 20.4. The inequality symbols does not matter that it's a less than or a less than or equal to, so please just keep that in mind. It does not matter if it's less than or equal to. So what we do know is that x bar is equal to 20, and we know that our standard deviation is equal to 0.25. So the first thing that I want to do is I want to convert 19.4 and 20.4 into z-scores. So I'm going to write z is equal to 19.4 minus 20 divided by my standard deviation, which is 0.25. And when you put that into your calculator, you're going to end up with negative 2.40. Next, I'm going to identify my next z-score, which is z is equal to 20.4 minus 20 divided by 0.25. So 20.4 minus 20 divided by 0.25, that is equal to 1.60. So that is the first thing we do. We convert it to z-scores. The next thing that we need to do is we need to rewrite this as a probability statement using z's. So I'm going to write this as the probability that my z-score is in between negative 2.40 and 1.60. Okay, so now remember that whenever you have an inequality, a compound inequality, we're going to be working with the larger z-score and then the smaller z-score, because I want to figure out what is the area underneath the curve that goes from negative 2.40. So I'm just going to approximate where I think negative 2.40 is. This is a shortcut, a shorter way of showing your work, all the way to about 1.0 or 1.60. And I want to find this space in between. So what I need to do is I need to identify what is the probability that z is less than or equal to 1.60. Because what that's going to do is it's going to find the entire shaded part, including the part that I don't want, that is less than 1.60. And then I want to subtract away the part that I don't want. And the part that I don't want is the part that is less than negative 2.40. So I'm going to subtract away the probability that z is less than negative 2.40. That's the part I'm going to subtract away. So remember that this is the larger z-score minus this probability working with the smaller z-score. Okay, so let's go ahead and identify the probability that z is less than or equal to 1.60. So I'm going to go to where 1.60 is. Here's 1.6 and then 0, and that's 9.9452. And I'm going to subtract away my smaller z-score, and that's going to be at negative 2.40. So I'm going to go to where negative 2.40 is located. And that is at 0.0082. And when I put that into my calculator, I'm going to end up with 0.937. And you can put a 0 at the end if you want, that's fine. But that is your answer. There is nothing further for you to do. Let's go ahead and look at example number 7. This is our last example. And then we are finished with this lesson. So it says a company produces light bulbs having a life expectancy that is normally distributed with a mean of we're going to change this, instead of 200 hours, we're going to change that to 2,000 hours. And a standard deviation of 50 hours. So our x bar is equal to 2,000, and our standard deviation, that's going to be equal to 50. It says, what is the probability that a randomly selected light bulb will last at most 2,085 hours? So at most, that indicates less than or equal to. So we don't want anything more than 2,085 hours. So we want to figure out the probability that x is less than or equal to 2,085 hours, which means that we need to convert 2,085 to a z-score. So that is step number 1. I'm going to take 2,080, I'm going to write z equals 2,085 minus my mean, which is 2,000, and I'm going to divide it by my standard deviation, which is 50. So 2,085 minus 2,000, that's equal to 85, and 85 divided by 50 is equal to 1.70. So I'm going to change my probability statement to a z statement, and I'm going to identify what's the probability that z is less than or equal to 1.70. And as always, I'm going to make sure that I draw a little sketch just to identify what's going on. And I'm just going to approximate where I think 1.7 is, and I'm going to say that 1.7 is about right here. And we want it to be less than, which is awesome. That's the inequality symbol that we're looking for. So I'm going to shade everything below 1.70. So now I'm going to go to my z-table, and I'm going to identify where 1.70 is on my z-table, and that probability. So I'm going to go to where 1.7 is. Here's 1.7. And 1.70, so that is 0.9554. And I'm done. So the probability that a light bulb will last at most 2,085 hours, that is 0.9554. All right, let's go ahead and look at what is the probability that a randomly selected light bulb will last at least 2,085 hours. So that means greater than or equal to 2,085 hours. So I'm going to write the probability that we want x to be greater than or equal to 2,085. So remember that at least is greater than or equal to, and at most is less than or equal to. Now remember that in order for us to use our table, we need to use a less than or equal to symbol. So eventually we'll have to work with the complement. But before we do that, we need to convert 2,085 to a z-score. And fortunately for us, we've already done that. We've already converted it to a z-score because it's the exact same problem as what we already had. So we already know that our z-score is equal to 1.70. So I want to rewrite my probability statement as the probability that z is greater than or equal to 1.70. And because it's greater than or equal to, I need to change it to a less than or equal to, working with the complements. So I'm going to write the 1 minus the probability that z is less than or equal to 1.70, which what's nice about it is I already know what the probability of z being less than 1.70 is. But before I do that, let me make sure that I draw a quick sketch of the situation. And I'm going to approximate once again that 1.7 is probably about right here, and I want everything above that. So I'm not looking for a very large answer. But I'm going to have 1 minus 0.9554. And when I put that into my calculator, I end up with 0.0446. And that is our answer. As well as the end of this lesson. If you have any questions over anything, please feel free to email me. Otherwise, I hope you have a wonderful day.